Hi there, welcome to APES Chapter 14 lecture video part 2 right now. So let's talk about this chapter is on environmental health and toxins in our environment. This is the second half of our lecture today. Let's begin. Let's talk about organisms and their natural defenses against toxins. So what do organisms do to not get ill or not be affected by all these toxins around them? Well, we have skin. It prevents the penetration or the entrance of a lot of these things. Can they still get in? Yeah, they can get in when we breathe. They can get in when we eat. They can. Some chemicals are small enough to get through our pores and our skin. Scales, organisms that have scales, they're pretty tough, and feathers, they resist a lot of the uptake. They're more resistant to uptake than I would say than skin, but they all serve as a surface protector. What else do we have? Well, we can break down toxins. So when a toxin enters us, our body can break it down. The faster we break it down, the quicker we can expel it. That's usually how it works. Things that we can break down faster and expel quicker are things that are not fat soluble. If something is fat soluble, it can store in our bodies a little longer. Just so you know, fat soluble means it's hydrophobic or it dissolves in oils or fats. If it's water soluble, that means it would dissolve in water. Things that are fat soluble can store inside of our bodies and our cells longer. Okay, let's move on. So two types of exposure: acute, a lot at once, or chronic, low exposure for long periods of time. Both do damage. One, chronic exposure, it's hard to detect chronic exposure because it happens over a long period of time. Acute exposure, it's easier to detect. For example, someone goes into a fire, in a burning fire in a house, and they get a lot of smoke inhalation. That would be acute exposure. Someone who smokes a few cigarettes a week over the course of their life would have chronic exposure to that smoke. All right, that's a difference there. Now, what happens to airborne substances? Well, there's this thing called the grasshopper effect. It's also called global distillation effect. So what does this mean? It means that toxins evaporate, and they evaporate areas where it's sunnier and warmer. So they evaporate more south towards the equator. All right. So things towards the equator, near the equator, even where we're in San Diego, we're about 30 degrees north of the equator in San Diego. We're in areas that have a lot of sunshine. Areas that have a lot of sunshine have a lot of evaporation. So an area that has a lot of sunshine, you probably have a lot of farming also. So what happens is wherever there's farming, let's use this as an example, you're going to have a lot of evaporation because you have a lot of sunlight. Well, what is evaporating? It's not only water that evaporates, it could be the pesticides that they were using in that farming industry. They're also evaporating. Deposition means some of it falls back to the earth as rain. Right? Well, what happens in global distillation or the grasshopper effect? Grasshopper, think of it as jumping from one point to the next. Well, it evaporates at a lower latitude, like around, say, 30 degrees latitude near San Diego, where it's sunny and warm, where we're using pesticides for farming. It evaporates here, and then it drifts north, and it follows air currents, and it goes north, and it goes more north, and then it goes more north. And then it condenses and becomes a liquid and gets deposited somewhere else. So something may evaporate near San Diego and may end up getting dumped near Alaska. So if you actually go up to Alaska and test the tissue and of the plants and the organisms that live in Alaska, you will find high quantities of pesticide residue that was not used anywhere near Alaska. They're not growing. They're not having a lot of farming in Alaska. Well, why are these Alaskans? Why does the tissue of the everything around them have such high quantities of these pesticides that they're not using? That's because of the grasshopper effect or global distillation. They're evaporating where it's lower latitudes, where it's warmer. They're drifting where it's cooler, where they then condense and get deposited back as rain or snow, and then so the contents are falling in other areas. Northern areas are getting these chemicals. Okay, so they're transported north. Sad. So you go to Alaska, they got a lot of chemicals there and pesticides, and they're not even growing food there. Now, where do toxins concentrate? They very commonly concentrate in water. Why? They end up on the ground somewhere. It rains eventually, and they end up running off into a body of water, or they run into the groundwater. So common area where toxins accumulate would be in water. They concentrate in water. Now, chemicals, some of them persist longer than others. Ideally, it's healthier for us for something to break down quicker because then it won't have a higher likelihood of making us ill. They break down into products called breakdown products. Some of these breakdown products are also harmful for us. So, like I said, the quicker they degrade, the better it is for us. They're not around as long. And by the way, this is an important thing you need to know. What can increase degradation? So factors that increase things, speeding up factors, temperature, moisture, sun exposure, these are all things that can increase the speed at which something will degrade. Now, what do toxic substances do? They accumulate, they build up inside of organisms. So we have these toxic substances around us, and they start building up around us. So then we start eating the substances around us. So they start building up in our tissue. They accumulate in our tissue, right? Things that are fat or oil soluble are absorbed and stored in body tissues very easily. They accumulate the easiest. They build up the easiest. Things that don't break down very quickly accumulate the easiest. They build up the easiest. These substances build up in the tissue of organisms, and then they get eaten up the food chain, and then they accumulate in the next level up the food chain also, right? So when organisms are eaten, these accumulated products or toxins are passed along from predator to prey in successive feedings. Now, as you go up the food chain, these accumulated products magnify as you go up a food chain. So, for example, let's go up a food chain. Zooplankton, they're in the ocean, and they're feeding on phytoplankton in the ocean, all right? And it's just showing you that something builds up in the water. It goes up the food chain. It goes up the food chain. It goes up the food chain. Up, and as you keep going up the food chain, it multiplies out. So look what happens. So this is toxins in the water, very low, 0.0000003 parts per million. That's a very small amount of toxin that's floating around in the water. In this case, the toxin is DDT, what Rachel Carson wrote her book about. So in the water, very small amount of DDT, not enough to make you and I can drink this water all day. We're not going to get sick. But then you go up, a feeding takes place, and it goes up. Look how much it multiplies. Now, zooplankton have 0.04 parts per million in their tissue. It goes up. Small fish have 0.5 parts per million in their tissue. The large fish, 2 parts per million in their tissue. The osprey eats these larger fish, 25 parts per million. So the water has very little toxin in it. The osprey, which eats fish out of that water up the food chain, has 25 parts per million. So it has magnified up the food chain, and it's magnified a lot. Okay? It magnifies a lot as you go up the food chain. This is why you shouldn't be eating high-level feeders from the ocean. They generally have a lot of mercury. Mercury magnifies up the food chain. So if you're eating something like shark or swordfish or mahi-mahi or halibut, those are higher level fish on the food chain, and they are going to have high levels of mercury in them. And that is because of magnification. Right? What happens? Well, honeybees, for example. What's happened to the honeybees? This has come up many times in your book. Pesticides. So the pesticides are picked up by the plants, and then the honeybees are eating the plants. So they're accumulating these pesticides, and then they end up dying as a result of it. All right. It's not just pesticides. Antifungal agents are destroying decomposers. And decomposers are vital for soil health and nutrient cycle. So toxins are magnifying up the food chain, and they're causing problems. A gentleman by the name of Louis Guillette did a study. What did they do? They were studied, I'll show you a picture. They were studying these alligators, and they looked at the samples of these alligators, and they were wondering what was going on with these alligators. And they found high levels of atrazine inside of these alligators. Atrazine is a very commonly used herbicide. I believe it kills weeds. It's a weed killer. Why are they finding the alligators? Well, they live in the body of water where all this weed killer accumulates in water and runoff. It ends up in their body of water. Now, this atrazine is in their blood. The problem with atrazine, it is a hormone mimic. It basically converts testosterone to estrogen. It feminizes these actual alligators. Tyrone Hayes, this gentleman here, he did a similar study. He said, well, let's see what goes on with atrazine and let's do it on frogs. Frogs are known as what's called an indicator species. They absorb any toxins from their environment. They absorb them directly through their skin, through the pores of their skin. So frogs, because they absorb from their skin directly like that, they can indicate toxins in their environment. So they basically tested these frogs and they contaminated their water with atrazine and they feminized them. What does that mean? Their testicles were shrunken. Their sperm counts were decreasing. So it basically made them less masculine as a result of their testosterone being converted to estrogen. So it's showing you that atrazine is a commonly used herbicide. It's a weed killer, and it is a hormone mimic, and it does damage to the sex hormones. It affects them. And if it's affecting them in frogs and alligators, it's probably doing similar things to humans. How do we study these things? We generally do what's called an epidemiological study. What does that mean? We do large-scale comparisons. Statistics are evaluated, and they're case histories. They look like histories of cases. So the reason we keep stats on so many things is we can use the stats to make inferences on what's taking place. So these studies or these case histories, they're generally very large studies. For example, people believe that vaccines lead to autism. A very large case history and epidemiological study was done, I believe, in the Netherlands. It was just a couple years ago. I believe it included 500,000 children that were born in the country over the last, X number of years. What they did in the Netherlands, they looked at all the children born in their country and how many of them were vaccinated, and they compared the vaccinated versus the unvaccinated to see the results of how many people developed autism. The study concluded that autism was not linked directly to vaccines. They actually had a higher incidence of autism in the unvaccinated group, actually, in their study. It was not a small study. It was a huge study. I believe it used about 500,000 births in children, and those are where they gathered all their data, and then they punched it all, a statistician punched it all on the computer and said, based off of stats, there isn't a direct correlation for vaccines and autism. Now, these studies can change over time, but that is the most current and the largest study done to date on linking vaccines to autism, and it showed that there was not a link, actually. All right. This is similar to what I explained here, how they look at it. They're looking at risks and effects and future hazards. Basically, epidemiological studies, they're not natural experiments where you're controlling them. I explained it just now to you. They're pretty much done statistically, and you're looking at different groups, and participants are looked at that way. Now, what do we do to figure out how dangerous a substance is? And you need to be very aware of what's called a dose-response analysis. This is a common theme on an AP test, AP Environmental Science test. So these analyses, they look at the dose and the response that it causes. And I'm going to show you what a graph looks like in a second. And the response, the common one that we are going to be looking at would be deaths. So you look at the dose and at what point it causes death. So this is when we're looking at how poisonous something might be. All right. So you plot what's called a dose response curve. I'll show you what that looks like in a second. All right. So here's one type of dose response curve. What these curves are used to identify, in this case, if your response is death, you would be calculating what's called the lethal dosage that kills 50%, the LD50. So the 50% affected point is the LD50, or the ED50 in this case, the effective dose is causing. Excuse me for 1 second. I got to plug in my thing here. All right, guys. Plugged it back in there. Sorry. All right. So went forward very much. So let's go back to this. The LD50 is the lethal dosage that kills 50% of the population. So the dose is down here. This is the dose. So it's called a dose response curve. Dose is on the x-axis. Y-axis is the response. So we want to know the point at which 50% are, in this case, the LD50 that are killed. So you find the dose at 50% by following the curve. All right? The point at which a response begins to occur, this is called the threshold. So in this particular graph, the threshold is 0. As soon as you take any bit of this particular toxin, a response begins to occur. All right? Now, look at this one. This one shows you that at low doses, there isn't a response. Threshold is not achieved yet because there's no response until a certain point is reached. That's the threshold. So this is what a lot of manufacturers and chemical companies use to say that their products aren't bad for you. They figure out what the threshold is, and then they keep their dose below the threshold. The problem is that these chemicals can accumulate. So you may build up to the threshold point. They don't talk about that. So they try to keep them below the threshold that's calculated. So there's no response, and then a response begins, and then at which point are 50% affected or killed. That is the dosage that would kill 50% of the population. When we make these curves, we generally do them on using, like, for example, lab rats. And we look at the weight of a lab rat, and then we extrapolate it for the weight of a human, and then we'll say, well, if 5 milligrams will kill a rat, let's multiply it by a certain factor, and that means that much will probably kill a human. So you figure out the dose to kill a rat, and then you extrapolate it out for the weight of a human as compared to the weight of a rat. This kind of dose response curve is an effective dose. It's talking about an ED. This is a dose that's the dose that's causing an effect. In this case, the effect goes up, and then it starts to swing down where no dose or less effect is occurring. This is an awkward type of dose response curve. This isn't usually leading to a lethal dosage. It's usually leading to an effect of some sort in this case. And these types of curves occur, they're not common, they occur with endocrine disruptors commonly. Synergistic effects. Well, what does this mean? Synergy means the effects are compounded. So you don't just add up the effects, they're not summed up, all right? What happens is their effects aren't just added together, they can multiply out with each other. So when you total all the effects, it's much greater than just the sum of them, actually. It's multiplied out. So the reason this term comes up in this chapter is we're exposed by BPA, and then you're exposed to PPDEs, and then you're exposed to phthalates. You're talking about endocrine disruption. If you're exposed to all those things, your body's effects could be synergistic, which means they're not just adding those effects, they're multiplying. They're much worse on you as a whole. This right here is risk assessment and risk management. What is the likelihood of dying to these particular things? Okay. Some of these things, they change over time, but look, lower respiratory disease, 1 in 27. Well, I think this year with COVID, this number might be a little higher. It might be 1 in 24 now, or 1 in 25 now, all right? Heart disease and cancer is the most common way of death, all right? Most common way you're probably gonna die, these right here. These are showing them all right here. Motor vehicle accidents, falls, assault by firearms, drowning, exposure to fire. Look how hard it is to get exposed to fire right here. Yeah. Airplane accident when people die in an airplane crash, they always say, well, it's way more likely to die in a car accident. And that is absolutely true. Getting struck by lightning, very rare. So usually you assess risk. You're looking at the statistics. What is the likelihood of something to happen, or the probability? So assessing risks involves, well, how toxic is it? You do a dose response curve to see how toxic it is. And then you want to figure out the population, like, what's the likelihood of them being exposed to this risk? Managing risk. Well, who's in charge of managing risk? In the United States, it's the FDA, the EPA, and the CDC. They don't always have our best interests, and I'll tell you why. They're government agencies who are managed by people who worked in the private industry before they were government employees. Most of these people that run the FDA or the EPA or the CDC, a lot of them work for chemical corporations. So they do not want to do things that could hurt the chemical corporations that they used to work for because they hold stocks and retirement incentives in those companies. It's sad, but in the United States, the corporations own these government agencies technically. You don't hear about it, but it's true. They own them because the people that work for the chemical corporations, well, they get appointed to these positions. And when they get appointed to these positions, they do not want to mess up their own vested interest in these corporations. Well, there's two major philosophical studies and approaches to these chemicals and these substances. There's what's called the innocent until proven guilty approach and the precautionary principle approach. Here in the United States, we go by the innocent until proven guilty approach. I do not like it. It's not good for us. Why do I not like it? This means that we have to prove that something is bad for us. So these chemicals that get developed, they are innocent. They cause no harm until we prove that they're bad for us, which means they get used for years before people can actually put together laws or regulations that control them. It's not very good. This is what happens in the United States. In Europe, they use the precautionary principle. Corporation says, we have a new chemical that it's a fire retardant. Well, Europe says, prove to me that it doesn't cause illnesses. I want to see your studies that show that it doesn't cause illness. It doesn't have a toxicity. What's its toxicity threshold? What is it doing to people? What is it doing to living things? How does it affect them? Then once you've proved that, then we might let you use it. That's the precautionary principle. This is the safer principle. But corporations do not like the precautionary principle. It costs more money. They like the innocent until proven guilty principle. This way they can make a lot of money on it. Even if they find out that it's bad later, they've already made billions of dollars by that point. In the US versus Europe, this is a common point. The US, I just said it, innocent until proven guilty. The Food and Drug Administration, the Environmental Protection Agency, the Occupational Safety and Hazard Association, they protect us. But like I said, the main people that run these are appointed positions, and they're appointed by politicians who had campaigns, who had money donated to their campaigns. So these are appointees that work for the private sectors, then go into the public sector temporarily, and they do not like to pass a lot of regulations that affect their corporations. So it's sad. We are not really protected here in the United States. It's called the revolving door. The revolving door is where they work for the private sector, then they go into the public sector, then they go back out to the private sector, and a lot of times back into the public sector. The door keeps revolving with the same types of people who are protecting their vested interests in the corporation. So in essence, the corporations are running the government in the United States. TSCA, this is the Toxic Substance Control Act. This is basically in the United States, it controls industrial chemicals. It allows the EPA to monitor them, right? Many believe it's too weak. Well, it depends on who's in government. Republicans generally weaken it because they want to deregulate. Democrats, in some cases, will strengthen it because they want to create more regulation. So it depends. It's very politically driven. Okay. The EPA, what are they responsible for? The EPA has some major responsibilities, and this is telling you what they're responsible for. They have to examine the ingredients. They have to approve them. They have to let us know that something is healthy for us, safe for us, for the most part. The reason I say for the most part, they are protecting the corporations a lot of the time because the corporations donate to the politicians, and then the politicians appoint these people. And economic considerations are a major part of it. When I say deregulate, usually when you deregulate, you allow people to use anything they want, and that can mean any chemicals that they want, which means it could do damage to the environment. So deregulation generally leads to damage to the environment, but people make more money. So it's It's a catch-22. REACH, this is the European Union's method, and TSCA is our method. We mentioned this a second ago. Let's compare the two. That's why I didn't cover a lot. Look at this. Europe says industry bears the burden and proof to show safety. In the United States, the government bears the burden of proof to show harm. Okay, so and our government doesn't get involved until harm has become prevalent, majorly prevalent. All right. In Europe, more data on new chemicals are required from the industry. In the United States, few data on new chemicals is required. That's not good. In the United States, it's showing you how the US basically prioritizes things. They are not prioritizing things to benefit us humans. They are prioritizing things to benefit corporations. All right. Industry is allowed to keep trade secrets, so they don't have to tell us specific chemicals that they're using. In Europe, database will allow public access to chemical information. We want to know what's in it. Here in the United States, for example, you may notice an ingredient on food you're eating. It may say contains natural ingredients. Natural ingredients can mean a lot of different chemicals, some of which are not probably good for you. So the word natural doesn't necessarily mean it's good for you or healthy for you. So beware. And that's the US's method. TSCA allows them to use these things. All right. In the US, there's a term called GRAS, generally regarded as safe. That is a term the TSCA allows. So a lot of chemicals in the United States, they might say, oh, it's GRAS certified. That means it's great. No, that doesn't mean it's great. That means it's generally regarded as safe. That doesn't really tell you a whole lot. Once again, in the United States, the system is designed to keep information from us and not let us know what's happening. Where in Europe, they want you to know what's going on. They want you to have information so that you can make a better decision on what you're going to be choosing to use. And this is showing it to you again here. POPs, persistent organic pollutants. These are pollutants that the Stockholm Convention said, hey, we need to reduce these, if not completely, try to get rid of them. Let me show you a list of these chemicals so you're aware of what chemicals we're talking about. I've already mentioned DDT earlier. That's the toxin that was mentioned with Rachel Carson. Deodorants, dioxins. PCB, the city of San Diego and Chula Vista sued Monsanto. I believe they won their lawsuit last summer. Monsanto paid Chula Vista and San Diego, I believe, about $500 million to clean up our water. These PCBs were used up until the 70s. Monsanto knew that these chemicals were really bad for us, yet still used them. So the city of San Diego said, we have them all over our bay. Technically, they believe PCBs are all over the planet and in the tissue of every living thing. They are supposedly haven't been used since the 70s yet. They're all over the planet. San Diego sued and said, you've polluted our water, you've polluted our bay, and they won. And it was a problem because now Monsanto has to set aside money because other cities are probably going to sue also. So San Diego, I believe, won $500 million, $500 million to clean up our water as a result of PCBs. And these are those chemicals that are those POPs. They're persistent organic. A lot of them they're fat soluble, so they stick around and they accumulate in the cells of the tissue of different things. We'll stop there.